Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying homogeneous second-order linear differential equations with constant coefficients, but we finally address the possibility that the characteristic polynomial has only complex roots. So suppose we have this second-order linear homogeneous differential equation with constant coefficients, and it gives rise to a characteristic equation that has no real roots whatsoever. This scenario can happen when the quadratic equation yields no real solutions because it has a negative discriminant. If b squared minus 4ac is negative, well then, trying to apply the quadratic formula to our characteristic equation yields no real solutions. There are, however, two complex conjugate roots. Negative b plus the discriminant times I over 2a, or negative b minus the discriminant times I over 2a. I is this imaginary number or complex number that satisfies the equation I squared equals minus 1. Now when the discriminant is negative, b squared minus 4ac is negative, the two complex roots are definitely distinct from one another, okay? Because in the one hand I have plus discriminant times I, and in the other I have minus the discriminant times I, and that discriminant isn't 0. So it stands to reason that a fundamental set of solutions can in fact be given the same way, e to the r1x, e to the r2x. Now this conclusion is true. However, it does require us to take the complex numbers r1 and r2 and putting them up in an exponent. Okay? The original differential equation had real number coefficients and was presumed to be defined over the real numbers. And now we're saying that the solution is this complex valued thing, and that's a little weird to say. However, we're going to use e to the r1x and e to the r2x to create a different fundamental set of solutions that are real valued. So let's see how we can create a new fundamental set of solutions. Suppose in general, y1 and y2 are linearly independent, so it is not possible to express y1 as any constant times y2. We claim that these two functions are also linearly independent, y1 plus y2, and the constant I times y1 minus y2. We're not actually claiming these two new things are linearly independent from the original functions, just that they're linearly independent from one another. Now, if they weren't, if they were linearly dependent, it would be possible to express the first as a constant times the second. In other words, y1 plus y2 is some constant times I times y1 minus y2. Rearranging terms, we would get y1 times 1 minus ki equals y2 times negative 1 minus ki. Now dividing by 1 minus ki, we've arrived at y1 is some constant times y2. But remember, we presumed that y1 and y2 were linearly independent. It is not possible to write y1 to be a constant times y2. Therefore, since this line down here is not possible, neither is this one, and therefore these two functions are linearly independent from one another. Let's now see how to apply all of that to our situation. It would be nice, however, to refresh what our situation actually is. We have the homogeneous linear second-order differential equation with constant coefficients, and we assume that the characteristic polynomial has complex roots, in which case we could make a fundamental set of solutions using these two exponentials, where r1 and r2 are the two complex roots of the characteristic polynomial. But we might not be comfortable with complex valued functions being a solution to a real valued differential equation. However, since r1 and r2 are not equal to one another, these two functions are linearly independent. If these two functions are linearly independent, well then, these two functions are also linearly independent. That's what we just showed. So let's compute what those two functions actually are. So we need to do a little bit of initial algebra. Okay, r1 and r2 are given by these two expressions right here. And we are now considering e to the r1x plus e to the r2x, but also I times e to the r1x minus e to the r2x. Let's just denote the following. Lambda is negative b over 2a, and omega is b squared minus 4ac over 2a. This makes our two roots a little easier to work with, lambda plus or minus omega times I. So e to the r1x is e to the lambda x plus omega xi. Based on properties of exponents, I can split that up as e to the lambda x times e to the omega xi. And e to the r2x similarly splits up as e to the lambda x times e to the negative omega xi. So the two functions that we're now trying to work with are given by e to the lambda x, e to the omega xi plus e to the minus omega xi, and I times e to the lambda x, e to the omega xi minus e to the minus omega xi. This looks like a lot right now, but trust me, it's going to start simplifying nicely. What's going to make everything simplify nicely is Euler's formula. Now take it as a given, if you've never seen it before, that the following is true. E to the ix is equal to the cosine of x plus I times the sine of x. This is Euler's formula, a terribly important result that relates exponentials and trigonometric functions through complex numbers. Now if this formula is true, which it is, then we can start computing e to the omega xi plus or minus e to the minus omega xi. First term, e to the omega xi, so I get cosine omega x plus I times the sine of omega x, plus or minus. Second term, e to the minus omega xi, cosine of minus omega x plus I times the sine of minus omega x. But remember, cosine is even, so this cosine of omega x is the same thing as this cosine omega x. But sine is odd, so this sine of minus omega x is the opposite of this sine omega x. Now what this means is, if I add the two together, if I put a plus here, this cosine adds to this one and I get two of them, but this one cancels out this sine because I can factor this minus sign out. So the sine terms cancel out and we just get 2 cosine omega x. Now what if I took the difference and multiplied the result by I? Well, first let's consider the difference. This cosine will subtract this cosine and they will cancel each other out. But this sine will subtract a minus sign. In other words, I will have 2 I sine omega x, which I now have multiplied by another factor of I. So I get 2I squared sine omega x, and I squared is minus 2. So a fundamental set of solutions is given by e to the lambda x, e to the omega xi plus e to the minus omega xi, and I times e to the lambda x, e to the omega xi minus e to the omega xi. Now we've already simplified the parenthetical terms quite a lot. 2e to the lambda x cosine omega x and minus 2e to the lambda x sine omega x. Now this is a fundamental set of solutions, but I can multiply them by scalars and not affect linear independence. In other words, I can multiply the first term by a half and the second term by minus a half to get a more standard looking fundamental set of solutions of just e to the lambda x cosine omega x, e to the lambda x sine omega x. So we now have a way to write the standard fundamental set of solutions. When we have this linear second-order homogeneous differential equation with constant coefficients, but a characteristic polynomial with 2 complex conjugate roots, as a fundamental set of solutions we get e to the lambda x cosine omega x and e to the lambda x sine of omega x, where the 2 conjugate complex roots are lambda plus or minus omega I. In terms of the coefficients of the original differential equation, lambda is minus b over 2a, and omega is b squared minus 4ac over 2a. Now you can go ahead and check that this function here, where lambda is given by this and omega is given by that, if you compute its first and second derivative, which will require applications of the product and chain rules, plug it in here, you will in fact get 0. Similarly, take the first and second derivative of this, where lambda and omega are given by these constants, and the derivatives will require both product and chain rules. Plug it into this differential equation, you will get out 0. You can also compute by the Wronskian that these two functions are linearly independent. If you really want to avoid ever citing any complex numbers, you simply kind of declare, hey, here are 2 solutions, check that they work, check that they're linearly independent. But if you get comfortable with Euler's formula, we can see that it's not actually any different than our exponential functions. It's just 2 different exponential functions with complex arguments, simplified a bit to look like real functions. Well, let's take all of our new knowledge and apply it. Verify that e to the minus 2x cos 2x and e to the minus 2x sine 2x do in fact form a fundamental set of solutions for this differential equation. So we're going to go through all the work just this one time. Let's go ahead and let y1 be e to the minus 2x cos 2x, and y2 be that other function, e to the minus 2x sine 2x. Then I can compute derivatives. y1 prime is given as follows. This comes from the product and chain rule. I can factor out a negative 2. And notice that this is actually negative 2 times y1 plus y2. Here I have y1, and here I have y2. So y1 prime is negative 2 y1 plus y2. Similarly, if I compute y2 prime and factor out the common factor of negative 2, I end up with negative 2 times y2 minus y1. So, in attempting to verify that we have solutions to our differential equation, we let y1 be the first element of our proposed fundamental set and y2 be the second element, and we computed their first derivatives and noticed that they can be given in terms of the original functions y1 and y2. Now I need to compute second derivatives. Of course, y1 double prime is just y1 prime prime, and we already established that y1 prime is this expression here, so I just need to take its derivative. However, y1 prime can be replaced with this term, and y2 prime can be replaced with this one. Distributing and collecting, we get just 8y2. All the other terms involving y1 exactly cancel out. Similarly, if I do the same thing with y2 double prime, I take the first derivative of y2 prime. y2 prime is this, so its first derivative is pretty easy. Now I substitute what I know y2 prime and y1 prime to be. I look at what cancels out, and I get negative 8 times y1. So we've computed, for the two functions y1 and y2, here are their first and second derivatives, with a bunch of simplification and written in terms of the original functions. Now I can take this to the proposed differential equation. y1 double prime plus 4y1 prime plus 8y1. Well, y1 double prime was 8y2. y1 prime was 2 y1 plus y2 with a minus sign, so when I put that 4 in, I get that. And then I have 8y1 at the end, and once I distribute all of this out, we just get 0, as if by magic. Similarly, if I do the same thing with y2 double prime, distribute collect terms, we also get 0. So indeed, y1 and y2, the two functions in our proposed fundamental set up here at the top, are in fact solutions to this differential equation. Having verified that they're solutions, we do need to check that they're linearly independent. So we'll do it through the Wronskian, y1 y2 prime minus y1 prime y2. Now remember, we actually found a nice form that y1 prime is negative 2 y1 plus y2, and y2 prime is negative 2 y2 minus y1, so I'm going to plug that in there to the Wronskian. And I get negative 2 y1 times y2 minus y1 plus 2 y1 plus y2 times y2. Distribute all of this out, and you end up with 2 times y1 squared plus y2 squared. The sum of two squares can't be negative, and it can only be 0 if each of the two terms are 0. So the only way this Wronskian can be 0 is if y1 and y2 are both 0 at the same time. Now y1 and y2 are both exponentials times a trig function. The exponentials can't be 0, so the only way these could both be 0 at the same time is if cosine of 2x and sine of 2x are 0 for the same value of x. But cosine and sine are never 0 at the same time. Therefore, y1 and y2 are never 0 at the same time, and therefore this Wronskian cannot possibly be equal to 0. As a second example, let's find a fundamental set of solutions to the differential equation y double prime minus 3y prime plus 4y equals 0. Well, as we've been doing, we start off with the characteristic equation, r squared minus 3r plus 4 equals 0. We're going to hit it with the quadratic formula. The roots are given by 3 plus or minus the square root of 9 minus 16 over 2. That discriminant is negative, it has complex conjugate roots. Splitting it apart, we'll get 3/2 plus or minus root 7 over 2 times I. So if I set lambda to be that 3/2 and omega to be that root 7 over 2, we immediately get a fundamental set of solutions following from the formula we've worked out, e to the lambda x cosine omega x and e to the lambda x sine omega x. And there it is. Notice we already know that this will give us two solutions and they will be linearly independent because we worked it out in general. So there's really no need to check it again now. As a third example, let's solve the differential equation 2y double prime minus 3y prime plus 5y equals 0, but with initial values y of 0 is 3 and y prime of 0 is minus 2. Well, first let's find a fundamental set of solutions. So we set up the characteristic polynomial, 2r squared minus 3r plus 5. We set it equal to 0. We find the roots. The quadratic formula will give us two complex conjugate roots, 3/4 plus or minus root 11 over 4 times I. So using lambda is 3/4 and omega is root 11 over 4, we get a fundamental set given by e to the 3/4 x times the cosine of root 11 over 4 times x, and e to the 3/4 x times the sine of root 11 over 4 times x. So here's our fundamental set. Now, since we have found a fundamental set of solutions, we know that any solution at all to the differential equation must be some constant times the first plus another constant times the second. Notice both of these have the same factor of e to the 3/4 x. So we can go ahead and factor that out. It might be a little more convenient. It's entirely optional. So here is the general form of our solution. Having set up a general form of our solution, we can start to use our initial values to solve for what those constants are. So just by taking y of 0 equals 3, if I let x equal 0, this exponential becomes 1. The sine of 0 is 0. The cosine of 0 is 1, so we just get 3 equals c1. That's awfully convenient. Taking a derivative involves a couple of steps. We need the chain and product rules, but eventually what you get is this monstrosity. So here's the derivative. E to the 3/4 x times 3/4 times the quantity c1 cosine of root 11 over 4 times x plus c2 times the sine of root 11 over 4x minus c1 times root 11 over 4 times the sine of root 11 over 4 times x plus c2 times root 11 over 4 times the cosine of root 11 over 4 times x. All right, it's a mouthful, but whatever. All I have to do now is plug in x equals 0, and it's going to become pretty easy. Now, if I plug in x equals 0, we were given that y prime of 0 is minus 2. On the other hand, this exponential becomes 1. The cosine of 0 is 1, the sine of 0 is 0, the sine of 0 is 0, and the cosine of 0 is 1. So all we get is negative 2 is 3c1 over 4 plus c2 root 11 over 4. So we found the general form of our solution, and we've used our initial values to solve that c1 must be 3, and negative 2 must be this expression here. But since we know c1 is 3, we can quickly solve that c2 must be negative 17 root 11 over 11. Taking those values of c1 and c2 back to our general form, we can conclude that our solution must be e to the 3/4 x times 3 cosine root 11 over 4x minus 17 root 11 over 11 times the sine of root 11 over 4 times x. And we never would have found this just by guessing. Okay, so this technique really helps us find these solutions in a pretty straightforward way because we went through all the work of finding the general solution. Well, what have we learned today? For second order, homogeneous linear differential equations, constant coefficients, ay double prime plus by prime plus cy equals 0. We solve the characteristic equation and find the roots of the characteristic polynomial, ar squared plus br plus c equals 0. If there are two real roots that are different from one another, we just get two exponentials as a fundamental set of solutions. If there's a single real root, then e to the r1x and x times e to the r1x form a fundamental set of solutions. But if there are two complex conjugate roots of the form lambda plus or minus omega I, then a fundamental set of solutions is given by e to the lambda x times cosine omega x, or e to the lambda x times sine omega x. Altogether, anytime you have a linear second-order homogeneous differential equation with constant coefficients, the characteristic polynomial either has two real roots, one real root, or two complex roots, and now we know completely how to solve that in any scenario.